We're going to get started with our first speaker here. Our first speaker is Chris Griffith. He and I have spent a number of nights at Lick Observatory back in the day observing supernova, but he is now currently a project leader at the Aerospace Corporation. He's going to talk to us about the aerospace industry and you. And test it out here.
Yeah, cool.
Sweet.
Thanks, Jeff. Yeah, thanks to the. Is that good? Okay. All right. Yeah, thanks to ATDS for putting this on and allowing me to talk. So yeah, I'm Chris Griffith, project leader. I've been at the Aerospace Corporation for about 6 years now, which is, ages in terms of tech, but it's been really good to me. So, and I'm happy to talk to anyone about my experience. And I'll talk, about some of my work and stuff we're doing, but it's, I'm going to dive deep into sort of what I work on, which is space situational awareness stuff, which is very an astronomy type of problem. But my company does a lot of things, and so do a lot of other companies in this space, so to speak. So I'll try to touch on those as well. But this is a massive field, right? Anything from geospatial to telescopes to, satellites. It's all kinds of really, really cool problems that are looking for people like you to help solve. So just before I start, we are hiring at Aerospace. I think it's a great company to start in. It's a very academic company. I won't go into too many details, but I'm happy to talk. It's where I started and I've learned a ton. There's job postings, I think, on the ATDS website that I put up. You can reach out directly to me at myaero.org right there. We also have grad internships and undergrad internships that I think are a great opportunity, which I wish I knew about when I was a grad student, to come work for us for 3 months in LA or DC, get some experience and see if you like it. So I'm going to talk again about space situational awareness, right? So basically what the world I live in now is, how do we keep track of satellites in space? And this is a growing problem. It's crowded, so to speak. But the game has really changed very recently, right? Like with Starlink, and you see maybe the string of lights that you see in the twilight and maybe in your data, right? But they've totally changed the game, right? Like we are looking at disposable satellites, which is something that this world has not really dealt with. We've always done exquisite, launch one thing, have it up there for 20 years. SpaceX has really changed the game, where these are only up for a couple of years and they just keep replenishing, right? And they just launch these off in one launch. They'll launch 60 of these and they'll keep growing and growing and growing so they can, increase their bandwidth, sell their internet to the world, right? And so it's becoming more crowded, and it's getting harder and harder for places like the Air Force and other, companies to keep track of satellites. So the big problem is we don't want things to run into the International Space Station. We don't want things to run into each other. We want to make sure things are in their right orbital slots. And so, you think of a satellite sort of in a consistent orbit, but things are moving constantly. And so especially like with this Starlink example, right, they're not going to stay in that line. They're slowly going to drift apart, right? And we have to make sure that as they drift apart and they move into their orbital slots, they're not going to hit anything. And they're not going to, cause all kinds of crazy stuff, debris, all things that are really bad. And so, it's a dynamic environment, so to speak. And then they're also constantly moving to sort of stay in their orbital slots, right? You have gravitational movements from the moon that are causing things to get out of their orbital slots. And so they'll have to do slight maneuvers to stay in their slots. Anyone that's worked with a space mission is familiar with stuff like that. And so, yeah, the question comes down to is, how is the Air Force and communities going to keep track of all these things and make sure that space is safe? And then just at the bottom, again, aerospace as a whole, right? You have, SpaceX, you have all these small companies that are in this game now. You have, of course, the big ones, Lockheed. You have my company that's fairly big. It's a rapidly growing field, right? The game is changing. The government's trying to keep up and make sure that things are safe. And it's an exciting field. I hope I get that across. So just in general, like, how do we track satellites, right? On the right there is a telescope we have at my company. It's a 1 meter that's in El Segundo, which is our main campus. And we use that mainly to track satellites. It's automated. You can put in, say, I want to track this satellite tonight and see where it is and update it. And so that's sort of the world that I live in, is this optical. But there's also radar, right? So we use radar to track things such as low Earth orbit satellites. Good. Okay. Um, and so radar is a good way to do it. You can get really good range, right? You're always pinging things and you're getting a range. And you can also get velocities very rapidly too, because you can ping it twice and say, okay, how much has it moved? But the world that I live in is the optical world, right? And so that's where we're just looking for dots in space. And we're looking to say, okay, where is it? I'm at a certain longitude, it's at this RA deck. I can now sort of triangulate that and figure out, okay, where's that satellite now? Where's it going to be in the future? And then we'll constantly update the catalog to make sure that things are where they're supposed to be. And so some pros for optical, right, is you can do high altitude orbits. You can look at geosynchronous satellites, things that are very far away, tens of thousands of kilometers. They still, emit a lot of light, especially at night as they're tracking the sun with their giant solar panels. And then, but the big problem is you're not going to get range from an optical observation, right? You're just getting a PSF that says, okay, it's here, but I don't know exactly how far away it is. And so you have to use algorithms, and I'll talk about those a little bit, to actually fit a curve and do what's called an initial orbit determination to figure out, okay, exactly where it is and where it's going to be in the future. And so again, both radar and optical imagery are used to track satellites and update a catalog. And so you can look at those at spacetrack.org. They're published every day, basically, updated TLEs, they're called, two-line element sets, to basically say, okay, this is where the satellite's going to be and where it's going to be in the future. And so just diving into optical space domain awareness. So astronomers, generally operate telescopes. These are the same telescopes that astronomers use, maybe slightly smaller. But they're mostly used to looking at images in sidereal track mode, right? Where you're just tracking the stars because that's what you're interested in. When it comes to this world, we actually do what's called a rate track mode, where we're actually using the satellite to track the target. And so I stole this from an interesting paper in AppJ, where they're actually using similar techniques to what we use in SDA to track asteroids. And so in this case, you can see on the left, they have a sidereal track image where you see the stars are fixed PSFs, and that's sort of what you're used to. And you see that the asteroid is actually streaking. So it's streaking over multiple pixels. But then on the right, you have the same image where they've actually cleverly stacked things so that the PSF of the asteroid is fixed and then the stars are streaking. And so those are on the right, those are the images that we're used to, where we're looking to track a satellite, figure out exactly where it is by tracking it correctly, and then determining its location. And so in this case, like in our world, stars are noise sources, right? They're going to pollute your data, especially if a star streaks over your target. It's just like a nightmare. So there's all these interesting techniques that astronomers honestly have developed to figure out, okay, how do I find the targets in the sea of stars, especially when you're looking at the galactic plane where you have millions of stars, you have large backgrounds that I'll talk about in a second. But that's sort of the how we've sort of turned it on its side, is we're interested in the targets, not the stars. So here's just like something I stole from APOD, which basically just shows all the noise sources we deal with, right? So you're used to like looking at stars, you're like, oh, that's awesome. We don't do that. We want to get rid of those. So, and we also want to get rid of the same backgrounds that astronomers want to get rid of, right? Like air glow, zodiacal light, all these things. And so, again, you can see how similar this is to some of the astronomy problems that people are working on in the optical and near infrared regime. And so, yeah, so when you look at the galactic plane, you're going to get tons of background stars. So how do you get rid of those? How do you find all of the targets in your scene and subtract those stars? And so that's the interesting game that we play, given this optical SSA data. And some interesting things just for space-based stuff. So some problems that you might not be aware of, right? So we have things called straight light, which I'll get into in the next slide, where basically you have the sun near where you're looking, because you always want to be, you're not always looking, in the perfect time of day, like you would in a moonless night, for some exquisite astronomy data taking, nights. And so you'll get things like stray light that you have to get rid of. And I'll show an example in the next slide where, you're looking near the sun. And so you'll have light from that source, either the moon or the sun or the earth, that's polluting your image. And you also have zodiacal light, all those things that I was talking about earlier when it comes to space. And so here's just an example of stray light, right? So this is GOES 13, which is a weather satellite. So you can see it's looking down on Earth. You can see the outline of the United States right there. You can see New Orleans if you squint. So up in the right-hand side, I don't know if you guys can see this mouse or not, but you can. Okay, good. You can see there's this gradient across the image, right? And so what's happening is you're looking at the Earth at night, or like maybe twilight. Not sure exactly what time of day is from the satellite or from the US's perspective, but the sun is in the sort of top right corner of where you're looking, right? And so the sun is up here, and so it's causing that stray light gradient to come across as the light is reflected in your baffle, and then eventually hits your detector, right? And so this is a noise source that we have to get rid of. And so how do you get rid of that? There's different techniques, but we're always trying to push that stray light noise down, because we want to be able to look at all times of day, right? We especially from space, we want to make sure that things aren't moving when we can't see them. We want to make sure that things are where they're supposed to be, and so we're always trying to push down the noise and try to find still be able to observe things even when we have things like straight light. So SDA data reduction, right? This is very similar to what astronomers do, because guess what? This field was started with astronomers, right? So the same things that you maybe do in your data, flat field correction, bias subtraction, we're always doing that to again get rid of all that noise that we can. The SDA community uses a lot of the same tools, astrometry.net. We definitely use that. We even use the magnitude system, which sucks, but it is what it is. Makes my job harder for sure. Just imagine teaching a magnitude system to a non-astronomer, right? Like an engineer, it's just like a nightmare. Yeah. But again, the reason that is because this field was born out of astronomers, right? They had telescopes that were in the V band back in the day, and they were like, "Hey, what if you track these satellites for us?" And so that's it was all born out of the same brain. But again, so SDAs. So while this looks very familiar, we're faced with very unique problems that I think are a lot of fun, such as eclipse from the Earth's shadow. Right, you'll have a satellite that's you'll see and see and see, and then all of a sudden, boom, it'll turn off basically once the shadow of the Earth eclipses it, and so you get no optical light. Stray light removal, I talked about that, and also non-intuitive satellite light curves. Right, so this is a big field in terms of like how do we characterize satellites in terms of what attitude they're in, where all you have is a light curve, right? But satellites are very complicated shapes. They have a lot of edges. They have solar panels, so they get a lot of speculars. They're not, a diffuse, nice object. They have a lot of, variability in them, and so that's an interesting problem where you can try to maybe get out as much of the data as you can by looking at the light curve and saying, is it tracking the sun? All kinds of different questions like that. So yeah, just another interesting sort of tidbit that we work on as well. And so once it comes down to, once you have the data, right, and you've reduced it and you say, okay, I know my telescope is at this lat long, I know this target's at this RA deck, that's basically the data you're getting out, right? How do you actually determine, okay, where it is and where it's going to be? And so this comes into these algorithms that I touched on, which is initial orbit determination algorithms. And so basically, when it comes to optical, you're going to need multiple observations, either from different telescopes or different times. And basically what's going to happen is you get sort of this curve here over the course of its orbit, and you can basically fit that curve. It's a very easy way to put it. There's a lot more math involved, but and there's all different types of techniques that people use to do this. This is an ongoing research field as well, in terms of how do we determine where things are with only 2 observations. We're always trying to push down the envelope and make sure that, if we don't have all the observations that we're going to get, can we still, make a good estimation of where it's going to be? And so basically you can, again, the optical system will look at it a few times during the night, possibly. Do an IOD, you get the orbital element set. So that's a Keplerian orbit, right? What's its center major axis, what's its eccentricity, all those things. You can propagate it forward using propagators. There's many of them. You get an ephemeris basically saying, okay, it's at this position now, it'll be at this position later. And then you get this, the future look angles. And so there's this whole feedback loop, right? Where you're just constantly looking for things and constantly updating their position, where they're going to be. And so, yeah, so this is a kind of a cool area. If you like math, all that kinds of stuff, where you can look into how people do this and the new techniques out there that people are using. So I'll just end. Yeah, I touched on a lot of things there, but I think space domain awareness is really cool. It's a growing field. I think astronomers have the background to make an immediate impact in this. We've hired a few and they've been very successful. You just have the base for this type of stuff. Tons of interesting problems. I only touched on few of them. Happy to talk more about other stuff I'm working in this field, which again is exploding. Other interesting problems in aerospace too. So, right, so I just touched on space domain awareness, which is the world I live in. There's all kinds of stuff we do at my company and across, the country, right? Geospatial imaging. So that's, you have Google Maps, you're looking down. That's a totally different problem regime, right? So what I just talked about is you're fighting the noise to try to get as much signal out, which is a very astronomer-like problem. Geospatial is very different, and that was kind of a transition for me when I worked on that. You have so much signal, right? You're signal dominated. And so it's a different problem space, but it's really fun too, right? You can do all kinds of different stuff to look at that data, reduce it, get as much information out of it as you can. So physical sciences labs. So, again, all of these aerospace, they have labs. So sensor characterization is something a group of mine does. If you've, stuff that's going to fly in space, material measurements. So we're looking at what materials are on satellites. What's it going to look like in space, which is interesting. We also do tons of machine learning and data science, right? So like all the other fields, we're just inundated with data in terms of geospatial or SSA, as I pointed out here. And so everyone's trying to throw the same techniques that are out there in tech against these problems. And we're doing that too at my company. So it's really interesting time. Let's see. Yeah, the other thing, I don't know how much time I have left. I don't know, but a minute. Oh, sweet. Okay. All I want to say is so this is just a matrix for my company. You can just see how many different types of things that are out there in aerospace. I was once told, once you leave astronomy, not that you leave it, I'm here, obviously, but there's an ocean of other things you can do with your career, whether it's tech, aerospace, all kinds of different stuff, right? And you're going to hear about that today. Aerospace is definitely an ocean that you can dive into and just learn a ton. And it's been awesome for me. Just working with very smart people in different departments. It's basically like a university as far as I'm concerned. So tons of cool problems, something to look out for in terms of career path. So with that, I will say we have internships, which I already texted on, and I'll just leave this up. So yeah, that's it.
Any questions?
If there are no questions there, I have one. So is that okay? Yes, I can see.
Yep.
Okay. So I can totally see how an observer, an astronomy observer can fit like a glove in this case. Mm-hmm. Do you think there's a slight extra degree of difficulty for a theoretical astronomer, or okay, that's good to know.
No, definitely not. Yeah, so my background was X-ray astronomy, which is not this at all. And I work with a lot of theoretical physicists or astrophysicists that are into this. There'll be a bit of a learning curve, but again, you have that base, and all the astronomers we've hired at my company have been very successful. So I would say no. Yeah.
Hey, nice job.
Yeah.
Have you tried using radar telescopes to track these satellites or debris in space?
Yeah. So what kind of telescopes?
Radio telescopes.
Oh, radio. Oh, yeah.
So we see, reflections from satellites, international space stations when we do the imaging.
Yeah. So the question was, do we use radar to do this? And that's absolutely yes. There are dedicated radars that the government has to do this. To again ping off of things. So yeah, that's the other arm of this world is the radar part, and they do things in different ways, but they go hand in hand. Yeah.
Hi, thanks.
Mm-hmm.
You mentioned that internships is an opportunity for students.
Mm-hmm.
In addition to that opportunity, as a mentor of students that may be interested in going out of academia and industry when they complete their degrees, do you have any guidance to help make their education successful both in the academic side, but then leading into success in the industry as well?
Sure. Yes, the question was, as a mentor of undergrads or grads, how do you help people transition into industry? Yeah, so I honestly didn't know about these internships, at least at my company. That's a great way to at least put it on the radar for them. I would say, I think we talked about this earlier, getting them involved with just like Git or SVN repos, like how to do proper coding is very good. It's really nice when an intern comes in or undergrad, then they know how to work with a repo and stuff like that, because most of our projects, have a large code base, and I assume it's similar in tech. So that's really helpful. Yeah, and just having a solid physics background, especially in the aerospace world, is helpful. But I think, yeah, trying to broaden them and show them other opportunities, at least for a summer, to maybe get out of academia is great. Because we have some really great success with interns that either come back to get hired or, do other stuff. So yeah, I'm happy to talk more. Yeah, my brain's running a lot. So yeah, we'll talk more. But those are the ones that come to mind right now. So
Very good.
yeah, thanks everyone.
So, right, how do I get back? While Josh is setting that up and getting ready for our next speaker, I will mention something I didn't mention at the top that I probably should have was, in addition to ATDS today, for those interested in a wide range of careers, there are a couple of Beyond the Academy events that are put on by the AAS Committee on Employment tomorrow. They're in the afternoon. Forgive me, I forget the exact times, but they're on the schedule. There's a Beyond the Academy careers, astronomy powered careers panel. And then after that, there's roundtable discussions where a number of the data science speakers and organizers from today and a wide variety of other careers will be in the exhibit hall, just chatting with people and taking Q&A. And everybody's going to have a long and different answer to your question, my friend. And so please ask. And I personally love hearing that. I want to help mentors mentor people as well as possible. That's one of the reasons we do this, not just for the people that are interested in these careers, but the mentors of those people. Okay, so moving on, our next talk is from Riwaj Pokhrel, and he is a data scientist at Spot Freight, going to talk to us about synergies between astrophysics and logistics. And I believe he is one of our newest data scientists that's giving a talk at ATDS, so that's always great. We like to have a range of backgrounds and tenures. So Riwaj is online, I saw, so we will hand it over to him, and please share your screen, Riwaj.
Awesome, thank you so much, Jeffrey. You guys can hear me okay, right?
Yeah, hear you great.
Oh, good. Okay, for some reason my video is not working, but that's okay. Let me share my screen. Okay, you can see my screen?
Yeah, looks great.
Awesome. All right, hi everyone. I'm Riwaj Pokhrel. I'm a newly minted data scientist at Red Technologies, which is a software branch, like a sister company of Spot Freight. It's a freight company, so a logistics company. I made this transition about 6 months ago, actually 5 months ago. So things are still pretty new to me. And I had a lot of experience when making this transition. And now I'd like to share all those kind of experiences with everyone. So I'll be mostly talking about what the Spot does, what do I do in this company, how I made this transition, and what are the similarities between the technical work that I did in astrophysics and what I'm doing here now. It's a low-key talk. Feel free to interrupt me, ask any question. So Spot or Spot Freight, this is based in downtown Indianapolis. It's a logistics company. It's a third-party logistics company, also known as 3PL. So third-party logistics is 3PL. 3PL, what they do is they provide the shipment, the arrangement of goods from one place to another. It's like if a business wants to transport its products to a different place, let's say from manufacturing place to the distributors or to the customers directly or to warehouses, then we provide the logistics, all the services that they need to take goods from point A to point B. So not two third-party logistics company are the same. Not two companies provide the same kind of services. what Spot does is we have a huge network of carriers. By carriers, I mean truckers, most of the time. We have like years of expertise and networks, and we do things on scale. So rather than for the businesses to transport their goods directly, it will be more efficient for them and cheaper for them if they contact us and we help them to transfer their goods. So that's basically what Spot does in like a very hand-wavy definition kind of terms. Now, the benefit for the companies is that they can focus on their business needs, their core competencies, product development, and so on, and let us worry about the logistics-related issues. Now, a little bit of history. Spot was founded 2009 on January 8th. So today is the 15-year anniversary of our company. These two gentlemen here, Andrew Elsner and Andy Snake, founded this company in a small room. And since then, it has grown quite a bit. Currently, it's about a mid-sized company. It has about 700 employees. It has offices in 6 major cities in the US, and it's continually growing. The growth is very rapid. It's growing very rapidly. And we are always looking for other people to grow together with us. So right now we have office in Indy, that's the headquarters where I am right now, and then Charlotte, North Carolina, Tempe, Tampa. We have one in Chicago, and from this year we'll have one in Texas. And if you like working for a mid-sized company where you get to experience a little bit of this, a little bit of that, how things work, rather than in some big company where you are just like doing one thing every day, this may be a good opportunity for you. Okay, this is what I wanted. I wanted to work on a mid-sized company, and this is exactly what this company is about. I work with Red. So Red Technologies is the software branch. It's the IT-related branch for Spot. It handles everything data related. Okay, and it's also a proprietary software of Spot. That's what makes Spot so unique and so competitive, and it has grown so much in so little time. It has all the IT-related things. It has like apps for drivers, for the truckers, so that everyone stay connected. It has a separate portal for TMS for the customers and everything. It connects every logistics-related aspects together, and that's the great thing about the Red Technologies. What do I do here? What does a data scientist do in a logistics company? Is mostly there are a lot of issues that requires a data science related expertise or some quantitative analysis related expertise to work on the logistics industry. For example, in supply chain optimization, we use data analytics, predictive modeling, machine learning to enhance supply chain efficiency. What ways can we reduce the cost related with any operation, improving performance of like delivery and pickup, demand forecasting models, optimize inventory management. And there's a lot of things that goes in the logistics industry that requires a data science expertise. So there are a lot of other areas also, or a lot of other tasks that I have listed here. For example, route optimization, a package or a truck needs to go from point A to point B. What are the possible routes? What are the most optimized, most efficient way of doing the delivery, and so on and so forth. I mentioned something, logistics 4.0. This is related with Industry 4.0, which is the fourth industrial revolution, and logistics is a big part of this revolution. We say we have already entered into the fourth industrial revolution now, and it's another revolution because of the age of the artificial intelligence, the machine learning, neural network side of things that is making logistics industry very efficient and very time efficient. So a little bit of background where I come from and how I ended up in the logistics industry. Here I come from far away, a place called Nepal, where I did my master's in physics back in 2012. And then I came to the US, University of Massachusetts, where I did my PhD in astrophysics with Professor Robert Gutmuth. And then at the same time, when I was doing my thesis, I got a CFA fellowship. So I went to the Harvard Smithsonian Center for Astrophysics. You may recognize this picture up here, where I did my 2 years of thesis work. And then I went back to UMass and then did my defense there. Don't get fooled by the pretty skies here. It snows all the time in both of these places. Not all the time, maybe like more than half the year. And then I did 4 years of postdoctoral research at the University of Toledo. Snows quite a lot here also. But it was very wonderful years. I spent 4 years. And then at some point, after 4 years, like it was around last year, I had to make a decision. Okay, what do I want to do? I'm like 37 years old now. I have 3 kids, and what is my like financial future look like? What everything, like putting everything all together. And I decided that I had to make this transition. And then I moved into logistics. So now a little bit of synergies between these 2 areas. The first thing that I noticed after coming here, notice I'm only working for 5 months, so things are still new to me as well. But the one thing along the similarity lines was the geometry. So in logistics, we have to deliver goods from point A to point B, let's say New York to Los Angeles. And then when you are calculating the routes and the optimization and every aspects, the cost and everything, we have to take care of that projection effects because of the curvature of the surface. We need the idea about the knowledge about spherical geometry. Now, as an observational astronomer, for me, spherical geometry is very intuitive. I right away think about like azimuthal rotation and all those things. And then it comes very intuitive compared to someone who comes from a different background. They don't usually work with spherical geometry. It would be a tedious work for them. If I have to get a distance, for example, to optimize the distance, immediately I think, okay, this would be a Haversine distance and not like a Euclidean distance or something like that. So in some way, that's kind of a synergy that I thought was very helpful coming from astronomy. We do a lot of segmentations work in astronomy. One of the ones that I use was Voronoi tessellation. It's found a lot of times in nature, for example, from the wings of dragonfly to like skin of zebra and so on. And we have been doing this work in astronomy for a long time. In fact, the left image here, I didn't know about this. I just found it yesterday when I was making slides. This is from a book by Descartes in 1644, where they used the Voronoi tessellation for segmentation in solar system, which I found pretty interesting. The one on the right is pretty recent, which is a Voronoi tessellation for galaxy wave distribution. We've used this for segmentation purposes in astronomy a lot. And in my sector, our lead data scientist, Trevor, when he asked me about like, can you do Voronoi tessellation? I said, yeah, I've done that before. And then we did that work, and the effect is more optimized routes, more that help in dynamic price modeling in our machine learning models, which we have more accurate models now than what we used before. Similarly, I did some works on, for example, using Monte Carlo Markov chain to fit the probability distribution function in molecular clouds. I studied hierarchical structures in molecular clouds, so on and so forth. And I came up on a project here where I had to combine both of these and do kind of a hierarchical Bayesian work here. So again, when my lead data scientist asked me about whether or not I can do that, I told him I do that for breakfast because I've done it before in my work, and we do that in astronomy all the time. So, and then I did that, and then again found even more accurate predictive models which had better predictions than what we were using before. It's used often in anomaly detection. That's how we are using here. This is one of the terms that apparently people use in industry, like anomaly detection. And we do the kind of works that we are doing in the industry in astronomy also, but we don't call them with the same like terminology. So it's important to know what the same kind of works are called in non-astronomy related fields as well. Similarly, we do a lot of optimization works, right? So on the left is one of the star formation relation works that I did before. And the techniques that I used in the fitting, for example, instead of least square feet. I use something called orthogonal distance regression, which takes care into account of the uncertainties on both axes instead of just the y-axis. Similarly, to find the networks of stars that are close to a particular star, I use something called KD tree, k-dimensional trees. Now, in my current work in logistics, I am using all these things, and a lot of these things are quite new. So when I mentioned about KD3, it sounded like it's quite a new concept that I looked into literature and whether someone had used this before in logistics, and it's just quite new. So we bring all this kind of technical expertise, our work, which is kind of very new in logistics and brings a lot of value in our day-to-day work that we do in our day-to-day job. And optimization, now this is more like scaled version of the optimization. It's a route optimization. So we have shippers, they need to pick up the load from point A to point B. There are little like fulfillment centers where LTL hub is less than truckload hub, like consider it as a major fulfillment center, and picking and dropping up there. And then there are certain trucks who will only pick up and deliver certain kind of goods. Now they have to be arranged properly. And if they are LTL, that means less than truckload. So there may be products from different customers on the same truck. Now, how do we optimize so that all the products are distributed on time as the customer is requesting, so that all the needs of the customer, the shipper, the carrier, everyone is met together. It's a huge optimization problem. And then again, from the warehouses or the distribution centers to the customers or where they need to go. So planning all that, the idea, the work that we do on optimization builds a very strong foundation in doing that. In industry term, again, that is called operations research. We don't even hear that when we are doing like academic work. So it's very important to know, like we do a lot of works, but we don't know what they are called in industry. And in the resume, in the job description, they say like, expertise with operations research, and we think we don't have any expertise and we don't even apply. But like doing a little bit more research and figuring out what they actually mean is a lot helpful. For example, in one of the route optimization works here, where there are different constraints, like the constraints on the weight of the truck, for example, how many stops can the truck make, what are the number of pallets in the truck, so on and so forth. Design or optimize routes so that the distance, total travel distance by the truck and the cost associated with it is minimized. It's a classic operations research problem. And the base, the foundation you need for the optimization problem like this, we get from academia. We have a very strong foundation when we do, because we do lots and lots of fitting optimization works in astronomy. Before you make a transition though, this is the question I asked myself when I was just doing some kind of work up here. One day, and then I had to decide, do I really want to make a transition? And then I decided, what are the pros and cons of like staying in academia versus moving to industry? This is my list. This is what worked for me around that time. Your list may be completely different, I don't know. But I think it's important to be sure to know for sure that you want to make this move before you are trying to like Windows up and like sending applications everywhere. And for me, it was crystal clear that I had to make a transition at that point. Okay, so if you make this like similar list for yourself, it would be helpful for you. And if you decide that you want to make a transition, then this is the framework that I followed, that I think works for people. I got a job from the day of started to applying. I got a job in 40 days from the day of applying to receiving the offer. I got 2 offers at the end, and I chose this one because this sounded like more innovative work and more exciting work. And this is the framework that I follow and I recommend everyone, is first to develop a job search strategy. What kind of job you want? Do you want to go in a small scale, small companies, or a mid scale, or a big companies? For me, mid-size was what I wanted to go. Building a personal brand it may be on LinkedIn, just like posting or stuff like that, but you have to like have, this helps a lot if you have a personal brand. And a portfolio, which could just be a GitHub repository for all your projects. Try to link them with, on a large scale, how that connects with the data science. That would be very helpful. That's what I did. The second step is networking, gathering referrals. I spent quite some time doing that also. And then, so by that, I mean, I did that before I was looking for the jobs, since like last year or something. And then just connecting people, just let them know like, hey, I'm this and that, I have this degree, I'm trying to make a transition, like stuff like that, connecting with recruiters, for example, and just following up on their comments or just keeping up. Like if you are just sending connection request and not doing following, you are not actually networking, you are just connecting with people. That's not networking. So networking is very important because referrals is like the best way you can get a job in industries if you have a referral from someone in the company. And then preparing for interviews, what kind of questions they ask. Like if it's a very code intensive job, you may want to practice using lead code, HackerRank, and so on. And then finally, after you are all set in your brain, in your mind, like where you want to go and all those things, all the preparations, you can build your resume accordingly and tailor the resume for the job, everything you apply, for every job that you apply, and then start your job search process. This is what I recommend. I hear people who say like they have been applying for the last 6 months, thousands of jobs and haven't heard back because they don't start at the top here, they start at the bottom. They first build a resume, probably because this is the comfort zone. Okay, this is the work, writing about the work that they know that they have done. This is the kind of comfort zone. And I came from the same background, so I feel that nervousness connecting to strangers on LinkedIn and getting referrals and so on. But after I started to connect and asking for referrals, I found that this is quite known process. This is a very usual, very normal thing when you are trying to get an industry job. So there's nothing to be nervous about or worry about. So except for that, that was my last slide. That's my LinkedIn and contact info. I'm also mentoring on adplist.org. When I was trying to make this transition, I met very wonderful people in ADP List. It's like a 30-minute session where a mentor volunteers their time, and then a mentee who needs support, they come in contact, and then they chat for like 30 minutes. It can be very informal. And then just sharing experience. Most of what I do is I share my experience, how I made the move and how I got into this position and what kind of opportunities there are available in logistics industry. That's all I do. So it's kind of low key, but it can be very helpful as well, depending on where you are on your job search process. So if you are or if you are not in ADP List, you want to connect and talk more about my experience and other things related, please contact me through ADP List. It's free, and you can have as many sessions as you want. So it's quite wonderful. And our company is, as I said, mid-sized company and rapidly growing. The data team is growing quite a bit. There are always opportunities. Please look out in the website, Red Technologies or Spot Freight. If you see anything you are interested, you want to ask me about the position or chat more about it, then we can definitely do that, right? Okay, that's all I had prepared for. Thank you very much for your time. If you have any question, I'd be happy to entertain.
All right, I'll go back to the screen. Thank you, Riwaj. By the way, we have a Q&A on the Zoom, so Eva is monitoring that. So if you have questions there, we have to re-plug in. Oh, we lost it again. Jeez. That happened once before. Was hoping it wouldn't happen during the talks today. We're good. Okay, we're good there. Great. So yes, for the people attending online, there is a Q&A online. If you want to ask your questions there, that's great. Otherwise, yeah, any questions online on Zoom or in person here?
I have one while somebody else maybe works up the courage.
Please go for it.
So for this work, it sounds like you're moving from one problem to the next relatively quickly. So it's not, you're not fixed in solving one specific problem. So how much do you rely on existing, software that it's in libraries or public or anything like that? And how much is your own development? How much do you have to develop from scratch, essentially?
So far, I've been mostly using libraries. So for example, for Verona tessellation, I use the SciPy library. For any other kind of like KD trees, it's the things that I've already used before that I trust. I have tested them, I have published them, so I know they work. And I have to just make tweaks according to the business needs, keeping that in mind. And I have used that. And mostly, the most of work that I have done here was building a recommendation engine for carriers. Actually, I didn't even talk about that because that's a very huge project, requires about an hour. And the reason I have been able to go from project A to project B quickly and very efficiently is because I have done this kind of work before in astronomy, but in a different context. And I've been doing the same. I feel like I never actually changed the field. I'm still doing the same thing I was doing before, but just not in astronomy, but in logistics. And the technological ideas are absolutely the same. So the one project that I would say, I don't know, I should say I built from scratch, but I did a lot of data engineering work for that. In Databricks, we use Azure system here, and then like gathering all the appropriate data, building this recommendation system, collaborative filtering, neural networks, and everything. That's the one big project that I worked here so far. I would say that it is kind of building from scratch. So.
We have an in-person question. If you can't hear it, I'll repeat the question.
Hey, so what are the challenges you face during the transition from astronomy to data science?
I'm sorry, I didn't get the first part.
So what are the specific challenges did you face during the transition?
Yeah, with the transition part.
Oh, okay. Great question. So the number one challenge that I faced was not having enough networks. Because when you are doing astronomy, at least for me, we were like that, total shell, and our entire world was within what we were doing, our like advisor space and everything. I never even like attempted to look outside of that shell and see what's around in the world, what's going on, and like that. So that was my biggest challenge. And being absolutely from the academic background, networking was a huge challenge for me because, as many of us, we like to have our private space. I do certainly. And then just like, getting out and networking with people, sending messages to a stranger and like, hey, do I want an informational interview at your company? This sounds like a very good job for me. I'd be a great fit. Sending the first message, I thought about that for 2 days. Should I send it? Should I not send it? What will they think about this? They may think I'm too cheesy. This is, oh my God. I wish I had just clicked that send button right away, seeing how common that is in the industry. The imposter syndrome that we usually have, again, that was kind of a challenge to break that barrier. After I came to work here, I saw how smart people are here and how collaborative they are, like sharing ideas, generating ideas. It's not like I have to do all the work. Like we have a team here, and like what it really means to have a team and that collaboration and support, I only knew after coming into industry. So I wish I had known more about how the industry works, especially the data side of the industry works before coming here. That was a huge challenge for me.
One more question here.
Mm-hmm.
Hi, thank you so much for this talk and the information. I was curious, so it seems like this field has a lot of synergies specifically with your work, but I was curious, would you have any recommendations for finding other fields that pertain to other astronomical, I do a lot of supercomputing runs and stuff like that. So I was curious, how do you find fields that have those synergies?
First thing is to do a little bit of research on what kind of work they do in that company. We just had one talk just right before this one, Christopher's talk, which had a lot of synergies with astronomy. Again, it's a very similar concept. Like there also you have to do a lot of In terms of geometry, I'm talking like spherical geometry and so on and so forth, all the techniques and everything, models, like the last 4 years of my developing models for protostars, I can arrange that in a way that is applicable in any industry that are doing modeling. Okay, and a lot of these, we are so fixated on describing the things we do in exactly the way they are. But if we are looking for everywhere and trying to make that connection with the other works, if we are able to try to make that connection, like I do modeling of, like, let's say, I did MSD modeling, for example, and then just to know that how that can be connected with any job that is asking for modeling expertise, and to be able to explain that, if we just know that, then we can immediately make a connection. So I wouldn't give like one particular example of this company is very related with astronomy and this is not related with astronomy, because more or less, if you can find that connection with your previous work, with the upcoming work, then you can always find that connection. So I found that in logistics. Christopher found that in aerospace. Some people find that in like ocean related studies. There was a talk, I think last year in the ATDS section, that was very fascinating. Some people even found that connection with robotics. So if you are able to link those experiences, you can find the connection.
All right, let's thank our speaker again.
All right, thank you.
Thank you so much.
Okay, yeah, we'll just round out our first session here. We have our last speaker of the session, Chat Hull from AES.
All right. Everybody hear me okay and see the screen?
Absolutely.
All righty. There we go. Okay, well, thank you all for the opportunity to give this talk. My name is Chat Hull. I am a data scientist at AES, and I discovered actually, Riwaj, I am 321 meters away from you right now, 2.5 blocks up the street in Indianapolis. So we will have lunch soon.
Seriously, yeah, definitely.
Riwaj and I were on papers before, so it's a small community that remains small in certain ways as you move forward. So that's really cool. So AES is a large corporation, bigger than Riwaj's. It's about 10,000 plus people. We're operating in 14 countries, and we are an energy company. But that means a lot of different things, some of which I'll touch on as I move through this talk. So our motto is accelerating the future of energy together. This AES started 40 years ago, primarily as an energy generation company using what we term as thermal. One might also term it as dirty energy, coal plants, a lot of coal plants. We're getting out of coal by right now, 2027, and we're engaging very strongly in what's known broadly as the energy transition, where we're moving from carbon producing energy sources to carbon free energy sources. And that's one of the main driving goals of all the people across all the different kind of sub businesses of AES in all the 14 countries that we work in. The things that we focus on a daily basis: safety first, do everything with that in mind. We have highest standards and we do it all together. So this was, by the way, rebranding. All together used to be have fun. This is what the now around 90-year-old founder of AES said, that he kind of regretted having to have it rebranded to something that sounded less silly. But I really enjoyed the fact that it was have fun, and we do have fun here at AES. It's an intense company. We do a lot of things. We do them very fast. That is one of the things that I will say was one of the biggest shocks. And people have, it because you hear so many people who've transitioned into data science. They say industry's much faster, but it really is. And that was kind of a surprise, but it's been really, really fun. And as we say here in this slide, we're a next generation energy company working basing what we're doing now, in the energy transition on 40 plus years of experience in the energy space. And the question is, can we power the things that we love? We're in a moment now where electricity usage is really in the forefront as things are electrifying in order to green the planet. So can we power everything we love and green the planet at the same time? Absolutely. So energy company, again, it can mean many different things, but at the very basics, we work in these spaces that I'm showing you here. So on the top, green energy, solar, wind, and now a growing component of our portfolio is energy storage. It's basically gigantic battery packs. We have still some coal plants, which I don't list on here because we're getting out of them. We have natural gas. That's a big part of our portfolio now, both managing natural gas itself as well as natural gas power plants. So we consider natural gas, it's a cleaner burning fuel. It's kind of a bridge fuel as we move toward as much renewable energy as possible over the next few years and decades. We have some hydro facilities as well in other countries. And then on the bottom left, we actually have 3 utilities. One of them is here in Indiana. So when you ask somebody here or in Riwaj's office down the street, what is AES? They say, oh, it's a utility company. But actually, that's just one of the dozens of sub companies within the umbrella of AES. There's a utility here, a utility in Dayton, Ohio, about 2 hours away. And then one that I've actually worked with in El Salvador, which is a really cool business that AES acquired a little while ago. So producing power, moving power around, and then doing other things related to power, doing commercial bidding, optimization, all that sort of thing. And also constructing. My manager will say, repeat after me, AES is a construction and finance company, because that's a lot of what we do with these solar sites and wind sites with power purchase agreements. So there's a lot of things besides just producing power and just transmitting and distributing it that we do here at this company. And as you imagine, there are a lot of things to do. Just a couple of very basic data science slides, because there will be some of you who are really new to this. With data, we can, well, do just about anything. So as many people will tell you, if you are a company at all, you are a data company. You are an IT company. You are a technology company. Basically, any company that's competitive in the marketplace uses data. Data is an asset. It takes some companies longer than others to realize that. But ultimately, the ones that succeed do realize that, and then they leverage it. So we can do all these things, understand business processes, improve efficiency, find root causes, predict future events. That fourth point is nominally what I'm supposed to do under the job title of data scientist, but of course I do many, many other things, which I'm happy to talk with you all about later. And then ultimately we drive value for the organization, which is the fancy industry term that once you're in industry, you will start using. It just means to make money. All right, what is data science? I enjoyed looking at many, many definitions. I like these 2 short ones. So Amazon says that data science itself is the study of data to extract meaningful insights for business. I capitalized that B in business, which Amazon did not. I use that all the time as kind of a personification of upper management. All they care about at any company, including at AES, is using data, which they have now realized is an asset, to make money. So we have to use it in a way that makes things more efficient, drives more value, gives the energy traders better ideas of what to do. So that's the key of data science itself. Now, data scientists, what we do is we examine which questions need answering and where to find the related data. That's a Berkeley answer. Some of us in the audience went with me to grad school, so I just wanted to put that up there. But that's the fun part. And at AES, I didn't mention specifically that our team, it's a rather small one, 10-ish people in the US, distributed in a couple of different sites, and 20 to 25 globally in a number of different countries, primarily in Latin America and the US. We are an internal consulting team. Business, again, capital B, comes to us with problems, and then we help them solve them. And part of that is actually kind of iterating with them to figure out what they actually need solved. They come and tell you they need X solved, but maybe they need Y solved, but you need to help them figure it out with your technical skills, but also your communication skills, which, there's many ways in astronomy to develop those, which that was one of my favorite parts of astronomy was doing science communication, talking with people in different subfields. That will come in very, very useful, especially if you're in this kind of internal consulting type role, which is the role that we find ourselves in on this team. Broadly, what we work on, I just put our cool branded icons up here. We're in basically 3 groups. Smart grid and utilities. So that's the utility side that I mentioned that is just one small component of AES, but an important one. It's not only actual power lines and management of assets like that, where by assets, I mean, physical or data things that we own, like a pole or a line or a transformer. That's an asset. There's also the kind of smart things. You get the little Wi-Fi symbol in the house, your Nest thermostat that can be managed partly. The charging of your EV, depending on where you are, you can actually use the EV as a source of energy for the grid to smooth out the peak, say after everybody comes home and starts using a ton of electricity. There's a lot of potential in making the grid smart, using this IoT, Internet of Things kind of framework in order for the utility to talk to all the devices, maybe even down to your dishwasher in your house, so that it can do load management and make the usage of energy much more efficient without you really noticing it. So there's a lot of that going on. And there are also other more kind of commercial aspects. You can do call center management. You can, grade call center representatives' calls using a large language model. You can do a billing analysis and make billing more efficient. You could do what I did in the utility in El Salvador, which I'll talk about a little bit later, where we did customer profiling to figure out who's going to pay their bill the next month. So there's a lot in utilities. Moving to commercial, which I haven't worked in as much, there's actually quite a bit of what Riwaj talked about. There's route planning is actually in utilities as well, but also in commercial. There's energy trading. That's a big one for AES because we produce energy, but we can also trade it. And a number of other things in the space that one of my colleagues primarily manages. And I'm getting more into the one on the right, so smart operations. This is going to be my main focus for 2024. You can see the solar, wind, and batteries icons there. Also a little bit within the thermal generation, primarily natural gas plants. This is essentially helping our assets, where now asset means like an entire wind farm, or maybe the wind turbines within it, the solar panels within a solar farm, the different parts of a thermal LNG, liquid natural gas power plant. You can help do, for example, anomaly detection, or try and figure out when something is going to fail before it gets too bad. But the reason that we're really focusing on this now is because we're scaling dramatically. Like, you don't necessarily build 10 new natural gas power plants per year, but you might commission 10 or 15 or 20 or 25 new wind farms per year, all of which include dozens of wind turbines. And so you can see how that kind of scale, which we're already seeing in this accelerating manner, it's impossible for the people who we hire, the wind engineers or the solar engineers, to actually look manually through all of the possible sensors in all of the possible assets within those farms. And so we need to put models on top of very well managed data, that's a whole other topic we can talk about, which is data stewardship and general data management, so that you can actually do analytics across all the different wind sites or solar sites. So that's the general smart operations field that I'm working on now, and it's a lot of fun. There's a lot of big challenges there. And data process in theory, this is what you might see in a textbook or on a website when you Google what is data science. Well, you might think that you can linearly move through all these steps, where you start with business understanding. That's the part that I mentioned before that I really like, kind of iteratively talking with business to figure out what the problem actually is. They'll indubitably point you to a data source. Data understanding can be easy or incredibly difficult. I spent probably 3 entire months trying to understand the database for the El Salvador project. That was difficult. It's not always that difficult, but be prepared for that to happen sometimes, because that's just the way it is. And again, data governance is a big issue now as the data volumes are growing, and it's becoming more important to have data that are easy to understand. There are best practices that can be put in place for how to sort of prevent that kind of difficult data understanding phase from happening as you move forward. And then kind of meshing into the next one, data preparation and EDA, or exploratory data analysis. That's where your astronomy tools really come in there. Data prep can include cleaning. I don't always have to clean my data, but sometimes I need to, at least filtering. We're used to in astronomy. I was a radio astronomer, so most of the time you're just flagging data, flagging one channel, flagging one baseline, flagging one telescope. It takes a lot of time. You could automate it. You can do the same thing here in data science. And then ultimately you make tons of plots, just plots, statistical analyses, look for outliers. It's all very similar to what both theoretical and observational astronomers will have done in their careers. And then ultimately, this is the 80-20 rule. Like 80% is what I just talked about, and then 20% or maybe even less is actually building the model and validating it. We have some tools in particular, like AutoML type tools. One is H2O. It's a really, really nice tool for but accelerating this process of building a model and hyper parameter tuning. So that's when you're getting toward the end. The model then gets put into production. Model deployment, you might do it, you might not. It depends on your team. I'm still learning a lot about how to do this because it really is very different from building models and doing EDA, which is something that you'll have more kind of familiarity with from astronomy. Some very large corporations, you just hand it off to an ML ops team where they take your model and then they deploy it themselves using their best practices. But some, like our team currently, but maybe not in the future, you need to deploy it yourself. So there's kind of a gray line there toward the end, but that's what you do. What you actually do is this, going back and forth, circling around. It's not linear, but that's okay. Neither is research. Just one example project as I start to wrap up here. So I worked on well, I'm actually trying to deploy it now. In fact, I was just emailing with one of the managers of the tool that we use to try and deploy this because we've been debugging it. So this project was a kind of standard customer behavior project where the goal is to predict who in the AES El Salvador client base is going to move further into arrears, or rather not pay their bill or continue not paying their bill in the following 2 months. That's the goal. So you have here, this is really standard machine learning. Here at AES, we do primarily work with tabular data like this, although we have been getting into images more. I actually hope to be able to work on some of that this year. There's some really cool stuff that we're doing with satellite data. But basically, you have your key on the left, which is the ID servicio in Spanish. It's the service ID, basically a client. And then you have a zillions of features, or just a few features, depending on what your model looks like. The average total billed in the last month, or maybe the average consumed in the past month, et cetera. All the way to the end. Now, this is your dependent variable, or the Y, which is what you're trying to predict, which is whether they rolled forward or not. So that's how I set it up. That, of course, involved lots of feature generation and data understanding. This looks simple, but it's actually not. Here's the nonlinear process of how it worked. Again, you start with this data set here in this little can looking thing, the El Salvador data warehouse. This may be exactly what you need. It may not. In the case when it's not, you might need to do some intermediate tables, which you can look at here. What I ended up doing for this was taking these basically converted right out of SAP tables here on the left and turning them into one intermediate table per concept, like the gestiones de the service orders. The acuerdos cuotas, this is all in Spanish, which I speak and I'm able to speak at work, which is really fun. Acuerdos cuotas is payment plans. So you have kind of one table per idea, and then you can generate your features by just using those or joining them with the other tables that you create. And by the way, this is actually important. This is a lesson in denormalization of data, where you don't want to always query your raw database every time, because sometimes the database is not built in a way that allows you to do that without crashing BigQuery, which is what I was doing before. So there's lots of good learning that goes on. And then you do some filtering. This is, again, iterating with business. For example, some tables only had data starting in June 2021, so you have to filter all the other tables. This is pretty simple here. And then you get to the feature engineering. This was time-consuming, but really fun. You can challenge yourself and try to do everything in SQL. That's sometimes possible, sometimes not. The little black square there, that's Rasgo. Rasgo has recently pivoted to doing more Gen AI, LLM type stuff. But before, they still maintain a tool to do automatic feature generation, which I believe actually, they may never tell us, but I think probably includes LLM type models of their own in the background. But that was a really great tool for doing different look back times, the average amount paid in the last month, 2 months, 3 months, 4 months, 5 months, 6 months. And you can then check the feature importance of all those features to figure out which one is the best without having to write the SQL for each one. GitLab, obviously, that's one thing I will very strongly encourage you to learn if you have not already. That is very important to know basic Git processes to keep things under control in your code base. And then ultimately you get the feature matrix, which I showed you before. Looks simple, but comes from a complex process. And then we have H2O, which is a really fantastic tool. The only problem with it really is that it's not within the Google suite. We really have bought into Google. They're our main vendor. We use a lot of their tools. Their tools are fantastic. BigQuery is really, really good. That's where I have my experience. But H2O is equally fantastic. It's just, kind of connecting the tools is difficult. If you were to ask me what is the main difficulty that I've had in this job, it's using many tools and getting them all to connect. And I think that's kind of a pain point that we all have, and it's something that we will improve moving forward. But H2O is used to help you generate a model. It can do all kinds of things that you cannot possibly do in the 8 hours of your day, making mathematical features, combining the features that you give it, putting 4 or 5 different models together, depending on how interpretable you want it to be, et cetera. And then you get toward the end here, which is where I am with this project right now, where you're monitoring it with a tool like Terera or like ClearML. You're trying to score the existing model that's up in the H2O instance using something like eScorer. There's many, many things that go into this deployment part, which, as I mentioned before, you may or may not do yourself. Last slide, making the transition. In my particular case, so I kind of a similar case to Riwaj's, although I happened to be in Chile when I had to make this transition, it was really hard. Getting a job actually wasn't that hard, which was very lucky, but the personal side of it was hard. Maybe for you it'll be the opposite. Maybe getting a job in this economy is harder and the personal side isn't so bad because you're already living where you're going to keep living. But it will be okay. Even given how hard my transition was, I can say with certainty, things are better now. They'll be even better next year. And it's fun. So it's okay. Trying to adopt a growth mindset. So to answer the question that was asked to Riwaj from the audience, what was the hardest part of the transition? So not of like being in this job, but moving from astronomy to data science. I have, one of my own personal failings, in my opinion, is it's hard for me. It's really easy for me to finish stuff, but it's really hard for me to start new stuff. And that in astronomy, I didn't always have to, because you just kind of guide your own career, which is a really nice thing about it for people who have lots of self-motivation. And I had enough, but it was really difficult for me to dive into a new subfield or, dive into a new technical paper or learn a new coding language. So, but you have to do that, in industry, it's just not an option. And so I was drinking from a fire hose from day one, and it was very uncomfortable at the beginning because I just had to learn new things over and over that I might not otherwise have actually made myself learn had I still been in academia. But that's also okay. And if you kind of change your mindset, adopt the growth mindset that challenges are not obstacles, but they're learning opportunities, that's really key. And I've learned to really enjoy all this new stuff. And I looked at my 1,000,000-page annual progress report, basically the goals and objectives that we submit at the end of the year. And I probably did more in the last year than I had in the previous 5 years of astronomy. So it's cool. Tools, get ready for them. You will have a budget, and the budget will be used, and you will probably have access to tools. We're a pretty tool-happy group here. Maybe not. I'd have to talk to Riwaj and everybody else. Maybe not every team is like that. But get ready to learn them, get ready to use them, and get ready to manage vendors, which is interesting. Not always good, but sometimes fun. Take a boot camp if you can. I found myself with 2 kids in another country and a job I sort of had to keep doing, although academia was pleasantly flexible as I was making the transition. I was able to continue getting paid while still mostly doing the data science preparation. The logo that I'm showing here is from TDI. It's the Data Incubator, although I didn't actually write that down because it seems like they're not doing their boot camps anymore. That industry is transitioning very quickly and has been for the last few years. I know that those who did Insight Data Science in the audience know that that is also no longer. So if, there will always be good options for bootcamp style things. You just have to find them, word of mouth, look at reviews. But it really does help to have some external motivation. Obviously, you have to pay for it. I was lucky enough to convince my previous employer to pay for it with some grant funding that I had. Some people can do that, some people can't. So, you can figure out what works for you, but I recommend it personally. And finally, there are so many tools that you cannot possibly prepare for all of them. You can try, but then maybe your new company won't use the ones that you tried. In general, no Python, just know it. If you do boot camp and you already know R and you have to learn Python while you're doing it, it's okay, but it's hard. So know some Python. There's lots of good tutorials. No Git. There are still people who I know and work with who aren't particularly good at Git. It just makes their process slower. And I would learn SQL. I think SQL is super fun. Maybe not everybody agrees. It's not that hard, and you use it all the time. I think pretty much almost anybody will probably agree. And it's really cool, like in Google, when you're inside of the Google space, to not have to pull data, especially if it's millions of rows, into, we use Domino, for example. It's kind of like my Unix terminal is Domino, which is one tool that you may have never heard of, but it doesn't matter. Pulling data into pandas, manipulating it and shoving it back into SQL. It's just a waste of time if you could do it relatively easily within SQL. And it just gives me great satisfaction when I can do that. So those are my 3 tips. Happy to take any and all questions. And thanks again for the opportunity.
Got time for one quick question before our break, so either online or in the room. We got one in the room.
Thank you for the talk, and also thank 2 previous speakers to showcase the different aspects of data science. I have this question that most of us are trained to be astronomers. We are kind of self-taught data scientists or computer scientists or statisticians. So how do we compare with someone who are actually trained to be data scientists? What's the advantage and disadvantage of us compared to them?
Could you, I got 80% of it. Can you say the last sentence? So how do we compare to somebody who's trained?
Right. So how do we take, I didn't quite catch the last part of that, but yeah, how do we,
There are people who trained in themselves.
Right. Right. How do we compete with someone who's trained to become a data scientist as opposed to our path?
Aha, excellent question. So, it depends on which hiring manager you talk to, but I would venture to say that at least now, and maybe we can debate about this, but you're probably actually better qualified, even though you don't realize it, to be a data scientist when you're not trained to be a data scientist. Now, this is the perspective that we've had in, many of the people who are in this room and on this webinar. But, nobody on my team has a degree in data science. 0 people. We almost all have PhDs, a couple of master's degrees. One of the ones, in the new data scientist, the junior data scientist in El Salvador, is getting a data science master's degree. But basically, all the people I work with on a daily basis have chemical engineering degrees, electrical engineering degrees, physics degrees. I have an astronomy degree. So I wouldn't worry about it. There's still a huge learning curve, but I think even somebody coming from a data science master's program, maybe data science terminologies like AUC or drift or whatever will kind of roll off their tongue faster than off of yours, but you can still learn it. And they're still going to have a huge learning curve walking into the tool suite and the environment and the business knowledge environment of their new company as well. So I wouldn't worry about comparing yourself with those or thinking that they're going to be ahead of you. In fact, you may be ahead of them.
Let's bring our speaker again.
All right. Thank you, chat.